Hello, in this video, I'm going to talk about chapter 1.1, which is solving systems of equation. And in this section, we would talk about how to solve a systems of equation by elementary row operation and also the types of solutions that we have, including consistent and inconsistent, and how can we use elementary row operation to discover if a system is consistent or inconsistent. So let's get started. What is a systems of linear equation? System of linear equation basically is a set of equation. Usually we would write it as using a bracket like this to indicate that it is a system, not individual equations. So this system are all linear because the unknowns are xi, x1, x2, x3, xn. In algebra, you would usually use x, y, z, w, those as unknown. But in linear algebra, we tend to use x1, x2, xn like that. So it's a little confusing in the beginning because when you solve it, sometimes this 1, 2, 3, 4 gets into the way of the number, the actual number, but x1 is actually the unknown. And the coefficient of the unknown is named as A11, A12, like that. And you should be familiar with the fact that when we solve a system of the equation, we try to arrange so all the x1 is in the first column, x2 in the second column, xn is the last column, and then the constant term b1 to bn is on the right hand side. So this is called a systems. We use A to represent those coefficients, B to represent the constant. So that's the kind of the convention. And if we have m number of equations, so you would have n rows, and then you have n unknowns, so that would be n unknowns. These can be equal, can be different, okay? But you can still solve it. So what is the solution? The solution is a list. Sometimes we call it an order pair, not order pair, order list of S1 to Sn that makes the equation in the system true. So S1 would go to substitute for x1, S2 would substitute for x2, and it would make the important thing is all equation in the system true, not just one, but all. For example, I have a system of 3 equation and 3 unknown. Is written in the way where all the x1 is together or in a row in a same column, all the x2 is in the same column, x3 in the same column, and then we want to check if 1, 2, -3 is the solution. So when you are written in this way, we assume that the first is x1, the second is x2, the third is x3, is ordered according to the name x1, 2, 3. So let's check. How to check if it is a solution to the system is I'll plug in 1 and then plug in 2 for that, for 2, plug in -3 for 3. So this, if you add this together, would be 5 minus 3 is 2. So this is right. And it actually equal to 2. So then you do the second one, 2 minus 2 plus -3. So, and that is -3, and that's also okay. The third is 1 plus 2 minus 3 times -3 is -9. So it's 3 minus 9 is -6, and that's also true. So it is yes. This is a solution to the system. Okay. Solution set. So if there is more than one solutions, then you write in a set, which is, like this, and you describe the sets of all the lists. Equivalence. So two systems are equivalent if they have the same solution set. So if one system has the answer of 1, 2, 3, 4, the other also has 1, 2, 3, 4, then we call them equivalent system. Some more terms. So what are the possible solutions? A system of equation can have no solutions. You can solve it. We call it, well, later on we'd say that if it has no solution, it's inconsistent. And it could have one or many. So for either one or many, we call it consistent system. If it's one solution, we call it a unique solution. Okay. To solve systems of equation, there is different method, but the main thing that we talk about in chapter 1.1 is elementary row operation. and it is used using matrix to represent the system. So there's two terms that you need to know. One is called the coefficient matrix. The coefficient matrix is a matrix that contains only those coefficients. So but if you line up x1 in the first column, x2 in the second column, then a11, a21, so all the x1's coefficient in the first one, all the x2 coefficient in the second one, or the xn coefficient is the n1. So if you have n unknown, you would have n columns, and you have m rows. Okay, m rows. So this is a matrix. Matrix is just basically a rectangular table that contains arrays of number. And then for elementary row operations, we also have something called augmented matrix, which is actually the coefficient matrix plus the constant matrix and the last rows. In some books, they would draw a line to separate them, but you can also just write them as n plus 1 columns of matrix. Okay, so how do we solve a systems of equation? Of course, in the old day in algebra, you have learned how to use graphing to solve a system, especially if it's 2 by 2 or even 3 by 3 system. So you graph the two equation, and the point of intersection is the solution. Okay, point of intersection is a solution. The main thing that we want to use is something called the elementary row operations. So we will convert it into a upper triangular systems and then use back substitution to solve. So this is main things for 1.1 because this method also help us to show if a system is consistent or inconsistent. If it's inconsistent, it have no solution. So how do I know there's no solution? You can use elementary row operation to check. So first, what is elementary row operations? So elementary row operation is there's three operations that you can do in a row. Row is in the augmented matrix. So you convert your or you write your system as an augmented matrix, and then this is one row. Row 1, the second is row 2, the last is row M, right? And then you can pretty much do operation in the same row because one row is actually one equation, right? The first equation. So it's just that you can think of it as a shorthand of leaving the x1, xn behind, but just write the numbers. So the things that you can do is you can replace one row by the sum of itself and a multiple of another row. So if you want to replace a row, you can have you cannot change. Let's see. Yeah, you cannot if you're going to replace, you cannot change yourself, but you can add to a multiple of another row. You can interchange two rows just like you interchange two equation, and you can scaling. You can multiply all the entries in one row and change it. But remember, you cannot change a row at the same time at another row together. You can multiply by a number, change it, or you can add to the multiple of another one. Okay, there are other methods. In 1.2, we'll cover a full elementary row operations, and then there is inverse matrix, which used only the coefficient matrix, and there's Cramer's rule. So there's a lot of different way to solve systems of equation. Elementary row operation is useful because it can scale to any systems, any row. Okay, matrix has its limitations. Limited to n times n, like a square matrix. The number of row and columns are the same, like that. So how do I do it? To do it, your goal is to eliminate to make the this the row in such a way that the first one is the first most left top column is a non-zero entry, and then following that all the others are non-zero entry, but these are zeros. So these are the one that you want to be non-zero, but you will make anything that is following the non-zero zero. Okay, so in a way that gradually you have like a upper triangular. So this would be anything. So we call it the upper triangular system. So in the lower side is all 0. So basically from the top left corner, you want all the 0 over here, and then down next, you want all the 0 below it, and then you have another one, you want all the 0 below it. Okay. To make them 0, you either add one row with the other row to replace it so it becomes 0. I'll illustrate this later. And in order to have this being 1, you would want to make sure that you swap. If this is a 0, you want to swap it with another one. Okay. So for example, I have a systems equation like this. I want to write an augmented matrix, which is the beginning of the elementary row operation. So how do I do it? I would write, so this is x1, x2, x3 all lined up, and the constant all lined up. So I just copy it out. 1, 2, 1, 3. No, 2. 2, -1, 1, -3. You don't need to change the sign. So just this has to be on the right-hand side of the equation, and you just keep it. 1, 1, 3, -6. So this is called the augmented matrix. Some books use a dotted line, but you can skip it also. Another example, if I have an augmented matrix from a system, what is the original system? So the original system would become x1, x2 is, so I usually would go x1, x2, x3, and this is the b. Okay, it's the constant. So x1, no x2, plus 2 x3 equal to 1. And this would be 2 x2 minus 3 x3 equal to 3. And this would be x3 equal to 4. So this would be an example of an upper triangular system because, so see, this is non-zero. All the one below it is 0. This is a non-zero. Okay. And everything below it is 0. So in the next row, this is non-zero, and then we have a system. And all these are 0, so this is good. Why is it good? Because when you write it up, you can see that you can use back substitution really quickly to solve it. Meaning now I write it up, I will say, well, x3 is already solved. So I can solve x2 by saying 2x2 minus 3 times 4 equal to 3. So 2x2 would equal to 3 plus 12 is 15. What? Oh, 4. Is this 4? Okay, so this is 3. Right, so x2 is equal to, gosh, is a fraction. x2 is 15 over 2, and then you can plug it in to x1, right? So x1 is plus 2 times 4 is equal to 1. So x1 is equal to 1 minus 8 equal to -7. So the answer would be x1 is -7, x2 is 15 over 2, x3 is 4. So you can see after you run it in, after you change your system into a upper triangular, you can solve it very easily by back substitution. And when systems are in upper triangular, when you're doing elementary row operation, you basically have an equivalent system, meaning the answer that you get for this system is the same as what you have before your elementary row operation. Okay, so I'm going to stop here and I will continue in the next video on how to do an elementary row operation and also how to solve it, as well as how to detect if a system is consistent.